Hello again. So today we're going to be talking about information that you can find out about the second derivative, about how that applies to a function. Specifically, we're going to be talking about concavity, points of inflection, and then we're going to look at how to graph a function using the information obtained from the first and second derivatives. Okay, so concavity is if you have an upward parabola like this, like y equals x squared, this is concave up everywhere. And if you have a parabola going down, that is concave down everywhere. Okay. To be more specific about what do we mean exactly when we say something is concave up or concave down, it means that the first derivative on a concave up graph is changing as we move from left to right. It starts off negative, then becomes 0, and then becomes positive. So that the value of the first derivative is increasing, going from negative to 0 to positive. So the first derivative is increasing. Now, when a function is increasing, that means its first derivative is positive. In a similar manner, when your first derivative is increasing, then the derivative of the first derivative is positive, which means the second derivative is positive. Okay? So concave up is when your first derivative is increasing as you go from left to right, and that will make your second derivative positive. In a similar fashion, when the second derivative is negative, that means that your first derivative will be decreasing as you move from left to right. See, the first derivative starts off positive and then 0 and then negative. So it's positive, 0, negative. It is decreasing as you move from left to right. So if the first derivative is decreasing, then the second derivative is negative. Okay, so when the second derivative is positive, your graph is going to be concave up, which means that it looks like part of a concave up parabola. That's the way I like to explain it. You know, it might look like just one part of it, like maybe if the function was decreasing and concave up, that describes the left side of this graph. It is decreasing and it's concave up. Whereas the right side of this graph is increasing. It's going up, but it's still part of the concave up parabola. So this is increasing and concave up, and this is decreasing and concave up. Similarly, the left side of this is increasing, but the whole thing is concave down, whereas the right side is decreasing and concave down. In other words, the first derivative determines whether the function is increasing or decreasing. The second derivative determines whether the function is concave up or concave down. And this shows that any of the combinations of increasing and decreasing with concave up or concave down are possible on a graph. You know, these would be the 4 different combinations of values of the first derivative and second derivative when we're just thinking about whether they're positive or negative. Okay, so what is a point of inflection? A point of inflection is a point on the graph where the concavity switches signs from positive to negative or negative to positive, either way. Okay, so these graphs have no points of inflection because they have no changes in sign of the second derivative. You know, we need to have a graph that is concave up for part of it and then concave down for another part, and the place where it switches is going to be that point of inflection. So let me show you a graph that has a point of inflection. This graph has a point of inflection. Now, points of inflection are not so obvious exactly where they are, like a local max or a local min, but I would estimate that it's right around there. Everywhere to the right looks like part of a concave down parabola. Everything to the left looks like it's part of a concave up parabola. So this is my best guess as to where the point of inflection is. Now, mathematically, if we want to calculate, where a point of inflection is, it's going to be a place where the second derivative, is about to change sign from positive to negative. And the way it's going to do that is it has to either temporarily be 0 or temporarily be undefined. So in a similar manner to first finding critical points, which is where the first derivative is 0 or undefined, and then determining whether they're local max or local min, points of inflection are found in a similar way, where you look at the second derivative, where it is 0 or undefined. You'll then make a sign chart, and those will be your, they're not called critical points, let's call them partition numbers of the second derivative. And then for each partition number, we're going to check to see whether the concavity switches, whether it goes from positive to negative or negative to positive. Either way, that's a point of inflection. But if it doesn't change sign, like if it goes from positive to positive, that's not a point of inflection. Okay, so let's look at an example. Okay, 3x to the fifth minus 5x to the fourth. Let's find where is it concave up and concave down, and where does it have points of inflection. So all that information is about the second derivative. So we're just going to take two derivatives and then analyze the second derivative equation. So the first derivative would be 15x to the fourth minus 20x cubed. The second derivative would be 60x cubed minus 60x squared. Then, just like the first derivative, we want to factor this so that we can easily identify where the second derivative is positive or negative. Or 0 or undefined, yeah. And then we'll figure out where it's positive and negative. So factor out a 60 out of both and also an x squared, and that leaves you with x minus 1. So the second derivative is 0 when x is either 0 or when x is 1. 0 and 1, now these aren't called critical points, I like to call them partition numbers. 0 and 1 are my partition numbers, and then I'm going to make a sign chart for my second derivative. Those two partition numbers we mark on our second derivative sign chart, and those two numbers make the second derivative 0, so I'll put a little 0 above them. Okay, and then we're just going to plug in numbers here, here, and here to see whether the second derivative is either positive or negative in each of those regions. Once again, we're relying on the fact that our second derivative is a continuous function, so that we can't have two different signs in one region. It has to all be one sign, either all be positive or all be negative for these three entire regions. Okay, so if we plug in like negative 10, a negative number squared is still positive, but this would be negative 11. So we have one negative, so the whole region is negative. If we plug in 1/2, that's still positive. 1/2 minus 1 is still negative, so this region is negative. And if we plug in a number bigger than 1, like let's say the number 2, everything's now positive, so this region is positive. So the function is concave down again, and then concave up. So only at x equals 1 is the concavity changing sign, or switching. So x equals 1 is the only point of inflection. X equals 0 is nothing. It's just a place where the second derivative is temporarily 0. You might not even be able to identify what that means on the graph, really. Okay. Let's back up a little bit, and let's look at the first derivative and see what we can find out about that, and then let's try to graph the whole thing. Okay. So looking back at the first derivative, I'll make the first derivative sign chart up here. We could factor out of both of those. Yeah, I guess getting a little bit ahead of myself, we need to factor this first. Factor out a 5x cubed out of both terms, leaving 3x minus 4. Therefore, 0 and 4/3 are our two critical points. Okay, so on my first derivative sign chart, 0 and 4/3 are the two values of x that make the derivative 0. And then I need to plug in numbers in each of those regions, and we're plugging them into the first derivative this time. When we plug in a negative number, we get a negative, because a negative cubed is still negative. And then this is going to be negative, so a negative times a negative winds up being positive. Okay, and if we plug in 1, That's negative, and so the whole thing's negative. And if we plug in, say, 2, everything's positive, so this is positive. So the function is going to be increasing, decreasing, and then increasing, which makes 0, where it's increasing then decreasing. That'll make that a local max. And 4/3, which is decreasing and then increasing, is going to be a local min. Okay, now I want to try to put this all together to try to sketch a graph of the function. Now, when I like to do these, I like to put these two sign charts sort of above each other. So let me shift this over a little bit to the right. And I want to line things up. So like this is 0 and that's 0. Okay, so I'll put that above that. Now 1 is a number between 0 and 4/3. Okay, and the second derivative is that sign chart. And when the second derivative is negative, that means it's concave down, concave down, and concave up, and 1 was our only point of inflection. Now, I'm going to try to sketch a graph of the function. But I want to have like at least a couple of points that are like accurate. Especially these 3 special points, 0, 1, and 4/3. So let's plot 0, 1, and 4/3. If we plug in 0 into our equation, we clearly get 0. If we plug 1 into our equation, we clearly get 3 minus 5, which is -2. Those were the 2 easy ones. Now, if I plug in 4/3, I'm going to get a huge mess. So I think I'm going to cheat, pull out my calculator. Okay. So we have 3 times 4/3 raised to the 5th power minus 5 times parentheses 4/3 close parentheses raised to the 4th power equals -3.16. That is an approximation. Okay. Now I'm going to try to put all my information together and sketch a graph of this function. So we have a point at 0, 0. We have a point at 1, -2. That would be right there. We have a point at 4/3. So 4/3 would be roughly there, a third of the way between 1 and 2. And -3.6 is roughly about there. So lining those up, that would be where that point is. Okay, 0 and 4/3 were maxes and mins. So that is a max. So there's a horizontal tangent line there because the slope is 0, and a horizontal tangent line here where the slope is 0. This is a max, so the function must be like going like that. And here that's a min, so it must be going like that. Okay, and remember, 1 was our point of inflection. That's the point where the concavity changed from being concave down and then switching to concave up. So now I don't know if it crosses at 2 or close to 2. This is just a rough sketch. So I believe that now fits everything about this graph. It was an increasing function concave down. Okay, that's good. Then it switched to be a decreasing function that's still concave down. Okay, that's good. And then at 1, where we now switching to concave up, but between 1 and 4/3, we were still decreasing. That's this little part right there where we're decreasing but concave up. And then last region, we're increasing and concave up. Okay, so that's how you do a rough sketch of a graph using the first and second derivative. It also helps to plot, especially the important points. If we wanted to find where it crossed the x-axis, we would want to factor this equation, and I believe the x-intercept we'd be looking for would be 5/3. So it's not crossing at 2, it's crossing at 5/3, which would be like more like this. So I guess it goes up a lot quicker than I had anticipated. Okay, let's do one more example. Okay, so let's look at the graph of f of x equals x plus sine of x, but I'm only going to graph it from negative 2 pi to 2 pi. If I graphed it everywhere, it would sort of start repeating. Graphing this should give you a good idea of what the rest of it looks like anyway, so we'll just restrict it from negative 2 pi to positive 2 pi. Okay, now let's say our goal is just to graph this, but in the process of graphing it, I will want to look at the first derivative to see where it's increasing or decreasing and where it might have local max and min, so I want to find critical points. And I also want to know where is it concave up or concave down, so I want to look at the second derivative to look at concavity. So we're going to do all of that. Okay, so the first derivative is simply 1 plus cosine x. Okay, so critical points. This isn't a polynomial, but critical points are where the derivative is either 0 or undefined. Well, cosine's never undefined, so there's no worry about that. Will this equation ever equal 0? So if you took this equation, set it equal to 0, you'd have 0 equals 1 plus cosine x. Solving for cosine x would equal negative 1. So when is cosine of an angle equal to negative 1? Well, on a unit circle, the value of cosine is the x-coordinate. So you're looking for when is the x-coordinate negative 1 on a unit circle? And that's at negative or positive pi or negative pi. Okay? And I believe those are the only two angles that are between negative 2 pi and positive 2 pi. So we have critical points at x equals negative pi and positive pi. Let's go ahead and make the sign chart for the first derivative. And because this function has this domain, I'm going to scratch off everything before negative 2 pi and past 2 pi, so that I don't accidentally try to plug in a number that's not even in our region. And these are only two critical points. For any angle between negative 2 pi and negative pi, now negative 2 pi would actually be equivalent to 0, and negative pi is this. So between negative pi and negative 2 pi is actually referring to the upper quadrants. And in the upper quadrants, cosine is positive. So a positive number plus 1 is definitely positive. Now an angle between negative pi and positive pi, actually that's any quadrant. So in any of those quadrants, cosine is either going to be some number between negative 1 or positive 1, but not including negative 1, because that's exactly at that point. So any number as small as negative 1 and as big as positive 1 would make this be between 0 and 2, but not including the 0 because we're not allowing cosine to be negative 1, therefore it's positive. And it ends up being very boring. Any angle you plug in, other than these two angles, which makes the equation 0, anything else makes the equation positive. Therefore, our graph is increasing and then has a slope of 0, and then it's increasing again, and then it's going to have another little slope of 0, and then we'll be increasing again. Okay, now let's look at the second derivative, which means obviously there's no local max or local min. Okay, second derivative is going to be 0 and then minus sine of x. Okay. I'm just going to think about this in terms of what does the graph of negative sine of x look like? It looks like the graph of sine of x, but flipped upside down. So it would look like that from negative pi to positive 2 pi. And therefore, this sign chart of the second derivative is negative, positive, negative, positive, with critical points or partition numbers at negative pi, 0, and positive pi. Negative pi, 0, positive pi. And negative, positive, negative, positive. Okay. Oh, and at these 3 points, that makes this equation 0. That's going to make all 3 of these points points of inflection because the concavity is changing from concave down to concave up or concave up to concave down. And either way is a point of inflection. Okay, so we have tons of points of inflection and tons of different concavities. First it's concave down, then it's concave up, then it's concave down, then it's concave up. Okay. Next, let's plot all of our important points, which are negative pi, 0, and positive pi. And let's also plot our 2 endpoints. So that's going to be these 5 points. If we plug in negative 2 pi into our equation, sine of negative 2 pi is 0. So we just get negative 2 pi plus 0 is negative 2 pi. If we plug in negative pi, sine of negative pi is also 0. So we just get negative pi. In fact, all 5 of these angles make sine 0. So it's just the value of x. Okay, that's boring, but easy to plot. I think I'll put my graph over here. So each of these are pi units. And so we have these 5 points on our graph. Okay. Then in this little region, which is right here, I want it to both be increasing but concave down. So I need it to bend like this. And at 0, we want to have a slope of 0. Yeah, this is probably the first thing you want to put on your graph, is any point where the slope is 0, do little horizontal tangent lines to help you remember that. And then increasing but concave down, so that's going to be bending like that. And then increasing and concave up, so bending like that. And then increasing but concave down is another region that looks like this. And then increasing and concave up is another region like the second region. You can already see that there's a little teeny repeating pattern. This pattern here just repeats here, and then it's going to keep repeating if we were to graph from negative infinity to positive infinity. Okay, so that is a sketch of the graph, and we use the first and second derivatives to help us graph. Okay, now, in terms of graphing, I've only done 2 examples, and there are some broader ranges of functions, especially some functions that maybe aren't continuous everywhere. Like rational functions usually have vertical asymptotes, or maybe we have other natural functions that have vertical asymptotes. So I think maybe in our next video, I'll be looking at graphing a broader range of functions rather than just the ones I've done so far. And we'll probably be delving into functions that require figuring out where vertical and maybe horizontal asymptotes are on a graph. So we'll be talking about that, and then we can graph even more functions using that knowledge. Anyway, see you in the next video. Hope you're having a good day. See you soon. Bye-bye.